Hello and welcome back. This is review video number 2 for my chemistry students. These are examples that I kind of already did together with you in class, but in case you didn't write them down or you were gone or you just want a refresher, I'm just going to go through these again. Percent composition. You did a lab where you heated a couple of substances that had water in their formula. You heated them to drive the water off, and we did a whole bunch of calculations by the percent composition that was actually water in these formulas. There's a few different ways to kind of do this. So I'm just going to go through these examples again really quickly. So in this problem, I'm going to underline 13.6 grams sample of a compound. So I already am thinking 13.6 grams is the whole compound. That contains both magnesium and oxygen, so that's important. And when it's decomposed, here's the other part, it says when it's decomposed we end up with 5.4 grams of oxygen. All right, and up here it says the percent composition from mass is the percent mass of the element. So in this case that would be the oxygen, right? Divided by the mass of the entire compound. I have to multiply it by 100 to get that in percent. This is super simple, right? 5.4 divided by 13.6 times 100, 39.7. Percent oxygen. That's what I calculated, how much percent oxygen. You can replay this if you need to. I'm just going to go very quickly through these because we've already kind of gone over it. All right, and then another example is we might be given a formula like C3H8, for example, and I might want you to calculate the percent of that formula that is carbon and the percent of that formula that is hydrogen. And you can see I haven't given you any grams or any amounts of anything. So this is more a theoretical, and you also had to do that in the lab that you did. You had to find the theoretical amount that was water based on the formula. So we need to find the molar masses of these. So I have to find the molar mass of this whole thing, and then I want to know how many grams of that are hydrogen and how many grams of that are actually the carbon. So I have 3, I'm just going to do these separately, 3 carbon and then all together so I need all of these numbers. So this is 44 is the mass of C3H8. So if I want to find the percent that is carbon, I simply take the carbon portion do my little calculation here. 36 divided by 44 times, let's see, just multiply that. 36 divided by 44, that's a completely different answer, times 100. I want that labeled. I want it labeled that I'm putting carbon on top. I want it labeled that I'm putting C3H8 on the bottom, and I want it labeled that this is 82% carbon. Please don't assume that I know that. I won't. I'm easily confused and I won't know that. So you have to tell me that. And you'll confuse yourself because too many times I see students get an answer and they're like 82 something. I don't know what it is, but that's the formula. So I want you to understand what you're doing, and by labeling it, that shows that you know what you're doing. All right. So it doesn't take a genius probably to think, okay, if the rest of that is hydrogen, right? So that's going to be like 18%, right? But I still want to see that you know how to do the math. Boom. And yes, it should add up to be 100. Check your math. Make sure that that's correct. And that's percent mass from formula. So that's a lot of times, again, theoretical percent mass. One extension that we can do with that, if you've already calculated the percent composition, this can be applied as a conversion factor to find out or obtain the mass in grams of each component. So what if I already know this. I already did this part, so I know that in this formula, 82% carbon and the other 18% is hydrogen. What if I have 125 grams of C3H8 and I want to know how many grams of carbon are in this formula? Super simple. I have to go back and say carbon is 82%. I can multiply that by, I'm going to convert the percent to an actual numerical value. And it becomes 0.82, and then 125 times 0.82, 102.5. Are the grams of carbon. I could do the same thing for hydrogen. Sorry, that's not grams. Oh my goodness, 125. I'm trying to go fast. These videos are limited to 15 minutes, so I go kind of fast, and you just need to pause it wherever you need to do that. If I added those up, they should indeed be 125. Oh, maybe there's a little, maybe, did I get a wrong answer? 22.5, 124. Nope, that's right, 125. Got it. Boom. And this is, I'm not going to go through this one, but this is the same thing, only remember these formulas that have water. This means for every 1 molecule of barium chloride, there's 2 molecules of water. So this 2 means 4 hydrogen, 2 oxygen, and I have to, for the whole entire complete formula, I have to add all this together. As I was correcting your percent composition labs, I noticed a few of you did not get that you have to add this all together as one formula unit. And then if I want to know how much is water, then I have to find the mass of 2 water molecules, which is 36, divided by this entire, right? You see this molar mass is the barium, the chloride, and then we add the water into that as well to get that 244. Okay, then the last thing we talked about, oops, I can see I need to move this up a little bit, was empirical formula. So empirical formula is finding the lowest whole number ratio of elements in a formula. So this is the example. So I said, hey, if I have this formula, it tells me a lot about the structural formula. It's 2 carbon connected with 6 hydrogen and so on. But if I want to know just the ratio of carbon to hydrogen, that's what the empirical formula is. It really is a 1:3 ratio. So we could write the empirical formula as CH3. It's C1, but we don't put the 1, H3. So I want to go through an example of that with you. And again, kind of did this in class. So I am, in this case, I'm given percentages, 25.9% nitrogen, 74.1% oxygen. That's what we know. If I want to know, so I'm going to try to figure out my chemical formula from this. So I need to convert my grams to moles, but I really don't have grams, I have percent. So what I said is we just pretend if we have a 100 gram sample, then we could just make these grams, right? So I just make those grams and then I'm going to convert them to moles, and we remember how we do that. I'm going to do my math really quickly. There, this is moles. Now, This is the part, so these are the steps. The next part is divide each molar quantity by the smaller number of moles between all of them. I always feel like this is the step that students just don't want to believe that this could be true, but it is true. The smallest is 1.85. Switch colors. Boom. So what these numbers actually mean are the ratio is 2.5 oxygen for every 1 nitrogen. Well, we can't really have 2.5 oxygen. So we do, although the next step is to divide each molar quantity and these become the subscripts, but if we have to make these whole numbers. So this is 2.5. If I multiply everything by 2, and I'm just going to do that, times 2, that's the easiest way for me to get whole numbers. So that gives me 2 nitrogen and 5 oxygen. This, people, right here is the empirical formula. We don't know if this is the actual formula or not. We just know that this is the lowest whole number ratio. This is the empirical formula. All right, what if we had another little tidbit of information though? What if I had another piece of information that said, what is the molecular formula if the molar mass is 216 grams per mole? Well, I need to find the molar mass of this first. Let's see what this is. 2 nitrogen I don't know what 5 times 16 is. That 80 or 90 or 80? There you go. Looks like 108. Huh. Well, it looks like if I look at 108 compared to 216, this is double that. So I must have to multiply these by, this must be double. The actual molecular formula must be 2 times this, which is, boom. So the molar mass of this must be 216. And that, people, is empirical formula in a nutshell.